Okay, so we would like to prove the q-binomial theorem. By this, we mean the following identity, that 1 plus xq, 1 plus xq squared, and so on, 1 plus xq to the n is equal to the sum from k equals 0 to n of these q binomial coefficients, and choose k times k q to the k times k plus 1 over 2 times x to the k. Okay, so the proof that we're going to give is completely combinatorial. So we're going to look at the left-hand side. So the left-hand side, so forget about the right-hand side for the moment being. And the left-hand side foils to an expression of the form sum from k equals 0 to n of a sub k of q times x to the k, where let's see what happens. So these are polynomials in q. And basically, in order to get x to the k, we need to choose from k parentheses the term that has the xq. I mean, think of it as a distributive globe between these n parentheses. And from the remaining parentheses, the term 1. So when we do so, what we get is a power of q that reflects whose exponent is the sum of distinct numbers. And this way, we can get pretty much all partitions that are made up of distinct numbers varying from 1 to n. So, in other words, a k of q can be characterized as number or the generating function for partitions in k parts in k distinct parts. None of which exceeds n. So, in other words, what we have is k numbers that are between 1 and 10. And let's suppose that we arrange them into an increasing sequence like this. So we can also picture this partition put into a tableau, into a diagram, not tableau. So this will correspond to the number mu1. This will correspond to the number mu2, and so on and so forth. Okay, so the trick now is to consider new numbers. So subtract um, 1 from mu k, 2 from mu k minus 1, all the way to k from mu1. Obtaining this way numbers, so let's write them as lambda 1 will be mu1 minus k, and lambda 2 will be mu2 minus k minus 1, all the way to lambda k, which will be mu k minus 1. And we obtain these new numbers that correspond. So first of all, these numbers, lambda i's, are greater than or equal to 0. And they correspond to a partition of that has parts that do not exceed n minus k. So corresponds. So these numbers correspond to a partition of at most k parts. And I'm saying at most k parts because some of these numbers may be equal to 0. So let's say if mk was 1, then this number is equal to 0, which means that it's skipped because in a partition, we never consider the 0 number as being one of the possible summands. And the largest number that we will have, k parts, that do not exceed n minus k. Okay, so in other words, we're talking about partitions that are contained in the grid that has k rows and n minus k columns. And of course, how much is this? This q polynomial is exactly n minus k plus k, choose k, which is the same as n choose k as a q polynomial. So this tells you exactly that an sub q ak sub q is n choose k. Now, we also have to take into consideration that the sum of these numbers, the sum of each partition, has been reduced by this amount right here. Oops, sorry about this. I think I created a symbol that I cannot erase, but in any case, these numbers right here, and we know that 1 plus 2 plus all the way to k is equal to k times k plus 1 over 2. So in other words, these two polynomials are not equal because the q powers on the right have exponents that have been reduced by this much. So for them to be equal, we need to multiply them by q to the k times k plus 1 over 2, meaning the length of the partition lambda is going to be exactly equal to the length of the partition mu minus k times k plus 1 over 2. Okay, and this is precisely because these numbers were defined by subtracting the numbers 1 through k from the mu sub i's. So hence we have this formula, and that pretty much proves our theorem. So that proves that the left-hand side is precisely the sum from k equals 0 to n of the q-binomial coefficient n choose k times q to the k times k plus 1 over 2 times x to the k, which is exactly what we wanted to show. And that's all. Thanks for watching.